Okay, it's time to begin frequency response via Laplace transforms. Now, when I say frequency response, what is this talking about? It says if you have a sinusoid input, what is the nature of the sinusoidal output at steady state? When we apply steady sinusoidal inputs, generally nobody cares all that much about the transient. What they're looking for is the steady state solution, or if in the language of method of undetermined coefficients, the particular solution. All right. So we're going to do this. And so we're going to start with sort of our familiar differential equation here. Y double dot plus 6y dot plus 18y equals 9 times the input. And you'll note here the input is a sinusoid sine of 4t. So we got a 4 radian per second oscillation. Now, all we care about is what is the particular solution. How we get there, we know we get there. It's things settle out, but people just want to know what is the steady state solution going to be. And to do that, here's what we're going to do. We're going to get the magnitude and phase of the transfer function at 4 radians per second. So that means we take the transfer function right here. So we can just look at it and write it down, 9 over s squared plus 6s plus 18. And we're going to substitute in for s with s equals 4i. And so if we look here, that's what we have right here. Okay, so s squared, if you have 4i, becomes minus 16. If s is 4i, 6 times s is 24i, so on and so forth. And we can gather terms, and we wind up over here at 9 over 2 plus 24i. So now we've got to get the magnitude and phase of that. So we put in the proper value of s, and so now we go to get the phase. So if you look at this, so this is a complex number. It's really 9 plus 0i, and here we have a visually obvious complex number, 2 plus 24i. So the top, 9 plus 0i, always when we're doing these things, just picture plotting these things out. You can just do a little sketch, and you go, okay, over 9 and up 0. So if you look at that, the angle here to go out to this point would be 0 degrees. Then we have a plus 2 and a plus 24. All right, and so this is in the denominator, so we'll subtract that number off. So let's just put that to work. So here's the sine, the phase, or the angle associated with 9 plus 0i is 0 degrees in the complex plane. The inverse tangent of this complex number will be, here's the y component, the x, so 24 over 2. So inverse tangent of 12. And because it's the phase, when you're figuring this out, we always take numerator minus denominator. So from your work with complex numbers, you should be aware of this. Okay, so we have 0 minus the inverse tangent of 12, and that works out to minus 85.24 degrees. Okay, we need the magnitude. So the magnitude of the top is 9. 9 squared plus 0 squared, square root 9. The magnitude in the bottom, 2 squared plus 24 squared, square root. This works out to 0.374. All right, and now here's the neat thing. If you have a sinusoidal input at 4 radians per second, the steady state output will be another sinusoid at 4 radians per second. So that's already known. So if this has amplitude 1, you take the amplitude and multiply it by this magnitude. So since the magnitude was already 1, we just wind up sticking this down in here. So 0.34 is the amplitude. Sine of 4t, that just flies through, minus, and here's the phase shift, 85.24 degrees, and we'll convert that into radians, pi over 180. Okay? So here's the neat thing. This is the same particular solution, or steady state forced response, we found via the method of undetermined coefficients earlier. So here's what we have. For any input, whether it's a cos omega t plus phi, so your input could have a phase to begin with, okay? Or you could have a sine omega t plus some phase that's out there to begin with. The steady state output is take your original amplitude and multiply it by the magnitude of the transfer function. Then you put in a cos or a sine, all right? Then what was ever originally in here that the cos was operating on, omega t plus phi, they go in. And then you add the phase shift caused by the transfer function. Here's this phase we did. You can just pop them in here. So all you have to do is, if you know a sinusoidal input going into a system, get the transfer function, get the magnitude and phase at the frequency, in this case 4 radians per second, and stick them in here and stick them in there, and you're all done. That's the end of it. Okay? This is quick, it's slick, it's fast. All right. So I'm actually going to, here's where we describe what this is. We're going to do some more work with this here, but I'm going to end this video right here, and I'll see you soon.